to the lesson for graphing proportional relationships, day number 1. And proportional relationships is direct variation. And that's when two quantities x and y are proportional, and the relationship can be represented by the direct variation equation of y equals mx. And so sometimes they end up using a different variable for m. They might use k in some books, but here they're using m, because m stands for slope, is the typical variable we end up using. And so the way, when they talk about variables being proportional, x and y are proportional, basically what that means is if I went ahead and took the x and y values and wrote them as a fraction like this, y over x, that would equal my m value, m over 1. And so when I go ahead and think about that, well, slope, which is what m is the change of y over change of x. So that kind of makes sense. So let's take a look at our problem here. And one thing we'll notice is that whenever things are proportional, we'll notice that we have direct variation. The line, if we were to graph the situation, always goes through the origin. So we can't have a direct variation going through any other point on the y-axis except the origin. So it says the cost y in dollars of x gigabytes of data are on an internet plan is represented by this equation, y equals 10x. Graph the equation. So notice how they say the cost y. Cost y, okay, that's the y-axis here. And I see that it is in dollars. So I'm going to put a dollar sign there, and I'll write cost going down. So that's my cost. And then over here it says for x gigabytes. So the x-axis is going to end up being represented by number of gigabytes. And then I'm going to end up coming up with some intervals. And so it looks like my slope is 10. And so that means I'm going to end up having to go up 10 spaces over 1. So maybe I'll use 10 as my interval. So this would be 10, 20, this would be 30, 40, and so the next number up here would be 50, and so on. So this would be 60, 70, and 80, 90. So you don't have to write each of the intervals in there, just enough so I can see what we're going by. And then here maybe we'll go by ones, so I'll call this 2, 4, 6, and 8, and so on. And then when I graph it, it looks like it's going to end up starting at the origin because there's no number being added to the x value, and the slope is 10 to 1. So again, if you were to think about a table, and the y value represents the f of x, the function of x, and if we were to pick some values, my first value is 0. So I don't have any negative values because I can't have negative gigabytes. Well, 0, when I plug that in, I just get 0. So again, you can see that because 0 times 10 makes 0. If I plug 1 in, 1 times 10 makes 10. If I plug 2 in, 2 times 10 makes 20. So you can see how I would just end up going up like this on my graph, the way I have the values situated, the intervals for this. And so it's going to continue up, so I'm going to show that arrow going up. Then it says, interpret the slope. So when I interpret the slope is 10 to 1. So the 10 represents the y value. And so I have to look on the y-axis. Well, right here, the y value is cost. The x, or the x value, is represented by 1. Well, the x value is right here, number of gigabytes. So when I interpret the slope, I'm going to say that $10 is the cost of 1 gigabyte. So all I have to do to interpret that slope is use the numbers that are in the slope and then the words that are associated with that axis. So dollars was associated with the y-axis, gigabytes with the x. Let's take a look at the next problem. It says that the weight of an object on Titan, one of Saturn's moons, is proportional to the weight of an object on Earth. And so it says an object weighing 105 pounds on Earth weighs 15 pounds on Titan. So notice they tell me what y is. Y is the weight of an object on Titan. Okay, so we've got y equals mx. This is our formula that we're going to end up using. So I'm trying to solve for m this time because they want to know what they want us to write the equation. So they're giving us the y value. Y represents Titan. Maybe we should write that up here. Weight on Titan. And then we'll say x right here. It says x is the weight of the object on Earth equals weight on Earth. And this isn't weight of, but weight on. And so we go ahead and substitute in. I've got 105 pounds on Earth, so 105, and times by m, and then weight on Titan is 15. So if I go ahead and do that division, I end up with a fraction, and I reduce that fraction. So I'm going to take out a common factor. Let me rewrite what I had. I see that 5 goes into each of these numbers. And when I do that, I got 3, and then 5 goes into 10 2 times, and goes into 5 1 time. So I can reduce that one more time. I can take out a 3, and I've got 1/7. So my equation would end up being this: y equals 1/7 x. And so let's go ahead and graph what that represents. The y-axis was the weight on Titan. And then the x-axis was the weight on Earth. And so let's go ahead, and we've got the weight on Earth is, maybe go by, probably by tens here. I'm going to say that this is 10 right here, so this would be like 20, 30, 40, and this would be 50, 60, 70, 80, 90, 100. So I'm going to just fit that number there. So this is 20. Let's see here. Actually, I'm going to scoot that over just a bit. Change that. Let's call this one 40, 50. This is 40. This would be 60 here. It's going by 20s now. 80, 100, 120. And then over here, we'll maybe just go by tens. Let's say 10, 20, 30, 40, 50, and so on. So from there, I'll go ahead and go up one space. And I've got for each 15 pounds, so 15 pounds would be right about here, and it was 105 pounds. So 105 would be, this is 110, 105 would have been right about there. And so you can see that my line would end up going like this, in that direction. And so we need to interpret the slope, and so the slope again is the 1/7. So 1/7 is our slope. So the slope represents, the numerator is the weight on Titan, and the denominator is weight on Earth. And so what we'd say is 1 pound on Titan is equivalent to 1 pound, or 7 pounds on Earth. And it makes sense, because if you look at the original example, it was 105 pounds on Earth, 15 pounds on Titan. So how much would a chunk of ice that weighs 3.5 pounds on Titan weigh on Earth? And so let's go ahead and plug it in. So y equals 1/7 x is our formula. So y represents the weight on Titan. So we put 3.5 there, equals 1/7, and then times by x. So I'm going to multiply by the reciprocal to cancel out that fraction. So get those 7s to cancel. Do the same thing on this side. And when I multiply that, 7 times 5 makes 35. Carry a 3, 21 and 3 gives me 24. So 24.5 pounds on Earth is what that would weigh. So let's move on to the next problem, and it says that the distance y in meters that a 4-person ski lift travels in x seconds is represented by the graph y equals 2.5x. The graph here shows the distance that a 2-person two-person ski lift travels. And so this is the distance here and time over here. Which is faster? Okay, so we know what the rate of the four-person lift is. Four-person lift is equal to 2.5. 2.5, and then if we look at the units on the y value, it's 2.5 meters per and then second. So we want to see if what this one is. So let's start with this, and let's go up. We have to go up 4 and then over 2. So the two-person lift is 4 meters per 2 seconds. So I had to go up 4 and then over 2 to get that. And I was looking at the units that they're giving me on the graph. And so this is 2 meters per second. So in this problem, it shows that the four-person lift is faster. 2.5 meters per second is greater than 2 meters per second. So the four-person lift is faster in this case here. Then it says to graph the equation that represents the four-person lift on the same coordinate plane as the two-person lift. Compare the steepnesses of the graph. And what does it mean in context to the problem? So we've got the y-axis here, and this is going to be in distance. So I've got distance in meters, and on the y-axis I've got time in seconds, and I'm probably going to use the same units they have here. So I've got 1, this is 2, 3, 4, 5, 6, 7, 8, and so on. And then going on the distance side, I'll go, this is going to end up being 4, so it'd be 6, 8, 10, 12, 14, 16, 18, 20. So now I've got that labeled, and I can go ahead and just kind of follow what the graph here shows for the two-person lift. So it's just going up 4 and over 2 each time, so you can see that it looks like this, and it just matches that one. And then along that, let's go ahead and label that. This is the two-person lift. So we need to label which graph is which when we're doing these, otherwise we wouldn't be able to, the reader would have a hard time following along. So then we look at the next one. It goes up 2.5 this time. So up 2.5 would look like this. Up 2 and then a half space and then over 1. So it's going to be a little bit steeper. So I'm going to do maybe up, how about double that. Let's go up 5. So if I do 2.5 and I double that amount, and so I'm basically multiplying both the top and the bottom by 2, that would be 5 over 2. And so that would be easier to graph. So up 5 spaces, so 5 spaces would be here, over 2 spaces would put me right there. I'll do that again, up 5 spaces, so that's going to be right up here, and that's at 10, and then over 2, and putting me right there. And then I do that again, up 5 spaces, and then over 2, so you can see that line looks like this. Up 5 and over 2. So it's going to be just a little bit steeper. It's kind of close to the line as we go, as we're starting off, but then as time progresses, you can see how much further it's going to be than the two-person lift. So this is the four-person lift. And so then we're supposed to specify, what do we notice about, what does that mean with respect to the problem? Well, basically, the four-person lift has a greater slope. And so you can look at the slopes here. If I look at the slope of the two lines, I've got, so the slope of the four-person lift was 2.5 over 1, and then the slope of the other one was 2 over 1. So this was the four-person lift, and this was the two-person lift. Lift, and then this was the two lift. And so what we notice is that when we look at the graph, it's going steeper. So what we can say is, what does this mean? Well, the steeper the slope that is steeper has a quicker time in which it will reach its destination. And so that's kind of an interpretation of what's going on here. So basically what we could also say is the slope that is steeper is going to be the faster lift. Would just be another way to end up saying that. So those are the types of problems you'll see on the homework. Good luck.